20 years ago, a vision was turned into a solid glass and steel instrument called the Hale Telescope. It was the largest telescope ever built, with a mirror 200 inches in diameter. It had taken 16 years to complete. The men who built the telescope were hoping to reach out billions of years into space to discover the large-scale features of the universe and to bring into fresh focus the mysteries of the universe, its size, shape, age, and its beginnings. In December of 1947, Dr. Ira S. Bowen, who was to be the director of the combined Mount Wilson Palomar observatories, was among the first to see the images of stars reflected by the newly completed 200-inch mirror. It was a moment suspended in time. The world, it was hoped, was on the brink of momentous new discoveries. Have those dreams been realized? Has the immense mysterious universe that surrounds our planet been brought into fresh focus? Perhaps those who have been part of the history of the telescope can answer that question. 20 years have gone by. Dr. Bowen recently retired as director of this observatory.
To describe the last 20 years, it is necessary to go back still another 20 years, to the early 1920s. The excitement of the last 2 decades can only be matched by that period. There was a great debate in progress. Early telescopes had revealed numerous faint objects in the sky that looked like faint clouds, many having roughly spiral forms.
Photographs of the faint, hazy patches of light revealed little information about them. Some astronomers thought that they were small objects in our own Milky Way galaxy, while other astronomers thought that they were huge, giant stellar systems at large distances from the Milky Way. In the 1920s, the newly completed 100-inch telescope at Mount Wilson was the largest telescope in the world. Dr. Edwin Hubble was interested in solving the mystery of the unknown hazy patches of light in the sky. He turned the large 100-inch telescope to the brightest of these objects and began to take photographs of it through the telescope. The patch of light was in the region of the sky called Andromeda. The 100-inch telescope was powerful enough to photograph the outer regions in some detail. Hubble was able to obtain photographs that resolved some of the outer regions into stars. When early photographs were compared to later photographs, it was discovered that some of these stars varied in brightness. Later studies showed that a few changed in brightness regularly. Studies of nearby regular variable stars had in the past shown that their periods of pulsation were uniquely related to their absolute brightness or candle power. Comparing the absolute brightness with the measurements of the apparent brightness then gave a measure of their distance. From a number of measurements of pulsating stars, Hubble found the distance to the object in Andromeda was 680,000 light years, proving that it was indeed another system of stars outside our own Milky Way. Within reach of the telescope were well over 100 million other systems made up of billions of stars. They became known as galaxies. Hubble's photographs revealed the distances and shapes of a number of galaxies. And then he further examined them by different wavelengths or colors. Spectral lines in the light from distant galaxies, when compared with spectral lines from standard laboratory light, revealed the presence of known chemical elements. A further comparison revealed a shift in the spectral lines of the distant galaxies toward the red end of the spectrum. This shift, shown here by an arrow, could only be explained as the motion of the light source away from an observer. Dr. Hubble and his associate, Dr. Milton Humason, took many photographs of the spectral lines of many galaxies. These small photographic plates, which revealed redshifts and velocities, together with measurements of distance, unearthed one of the great secrets of the universe. The speeds of galaxies away from Earth were related directly to their distances from Earth. Astronomers came to the astonishing conclusion that we live in an expanding universe. The nearby galaxies were rushing away from Earth with relatively small velocities. The more distant galaxies had greater speeds, and the most distant galaxies the greatest speeds. If the universe was expanding, then perhaps there was a beginning to the expansion. Could astronomers see far enough into space to find clues to the beginnings of the universe? But they'd reached the limits of the 100-inch telescope and needed a much larger instrument. Dr. George E. Hale, builder of the Mount Wilson Observatory, obtained funds from 3 of the Rockefeller boards for a 200-inch telescope. He supervised the designing of the new instrument and enlisted the help of many distinguished mechanical, electrical, and even aeronautical engineers from all parts of the country. Russell W. Porter, engineer and astronomer, made up a series of drawings to illustrate the details of the huge new instrument that was to weigh hundreds of tons, yet move with the precision of the finest watch. Every detail was first drawn on paper, and then a 100th inch scale model was built to visualize the movements of the telescope, east and west, and north and south. Finally, a 1/10th scale working model was constructed, and the more critical calculations were subjected to actual tests on it. The project engineer, Bruce Rule, tried out the controls. The model, which later became a useful small telescope, had a 20-inch mirror that was cast and ground without difficulty. The first attempts to cast a huge glass disc for the 200-inch mirror from fused quartz were unsuccessful. The Corning Glass Works was then called in to make a disc of Pyrex glass. Dr. George V. Macaulay was in charge of the project.
We first prepared a mold into which the molten glass was to be poured. Ceramic cores were set in the mold. The cores were to be later removed to give the mirror a rib structure and the greatest stiffness for the smallest weight. A mixture of sand, boric acid, borax, niter, and aluminum was prepared and shipped to the furnace. When you talk about getting a 20-ton piece of glass perfect in all respects, that's a little too much to hope for, but it was foremost in our minds. The mixture was first brought to high temperature in the melting tank. The heated mixture, which was now molten glass, was ready for pouring into the mold. In 6 hours, 2 crews of men poured 42,000 pounds of molten glass. They emptied 400 pounds at a time from 3 ladles that ran on overhead trolleys between openings in the melting tank and pouring doors in the casting oven. In this oven, the glass was kept hot while casting so that the glass would flow freely through all the spaces of the mold and fill all the rib structure. The appearance of this oven resembled a large beehive, so it got the name of beehive. You're handling, say, 300 pounds of glass up to 700 or 800 pounds of glass in a ladle. And these ladles are not simple things either. Well, when you fill this ladle with glass, when you push it into the tank, it's buoyed up by the weight of the glass, just like a cork buoyed up by water and a ship's buoyed up by the sea. So they're able to bend down on their long end of the handle and raise it up out of the glass. And the whole weight of the glass then rolls down on this downhill support so they can handle the thing easier and roll it over to the other place and push it in the tank and empty it. We began work on the project of making this disc in late fall of 1931, and it wasn't until 1934 that this disc was successfully cast, and not until 1936 was it ready to ship to Pasadena. We were so glad that we were successful in making it and could ship it as one piece of glass. We were glad to see it go.
In Pasadena, the California Institute of Technology had constructed a large air-conditioned, dust-free optical shop. The front face of the glass disc was to be ground and polished to the incredible accuracy of 2/millionths of an inch or better. Melvin Johnson was one of the 21 opticians.
The grinding is done not only with different size abrasives, but also with various size tools. The grinding tools consist of small tile blocks cemented to a steel base plate. The final polishing stage is very critical. Any gritty substance on the glass or on any of the polishers could scratch the mirror and either ruin it or set the project back several years, perhaps. The red rouge of iron oxide, the final polishing agent, is diluted in water. The periods of polishing grow shorter and shorter and more critical as greater accuracy is to be achieved. This illustrates the necessity for circulating the rouge and keeping it in suspension of the water so that the polishing tool will have red rouge between it and the glass at all times. Otherwise it would seize up and cause what we call sleeks. Maybe perhaps even a small scratch could happen if it were to run dry. And so a man has to keep on the bridge circulating the rouge anytime the machine is running. The mirror was tilted up while still on the carriage of the grinding and polishing machine. In a vertical position, it faced a test platform 110 feet away. Testing a mirror to 2/millionths of an inch seems like almost an impossible job, but it was done very simply with a tiny beam of light. A small light bulb was enclosed in the housing on the right, which shines through the pinhole towards the mirror. A movable knife edge in front of the observer intercepts the returning beam of light. The adjustment of the knife edge reveals patterns of light and shadows, which in turn reveal the accuracy of the curvature of the mirror. It took 7.5 years of grinding and polishing and testing. 30 tons of abrasive and polishing compounds had removed 5.5 tons of glass. The curve in the surface didn't seem like it was deep enough for the amount of time we spent grinding it. However, we know that the depth of the curve was enough to give us all a bath. There's 36 supports. This is so that no matter how the mirror is tilted or rotated, each will carry its own share of the weight of the mirror. The mirror was placed in a steel cell, which was to be eventually bolted to the bottom of the telescope tube at Palomar. The lifting crane was carefully rigged to lift the ponderous weight without strain or jar. 35 tons of mirror was hung by 12 cables. How can I tell how much I worried about that? Everyone else of us worried. This was probably one of the most critical operations in the whole phase. We felt perhaps a lot more personal interest in it than we had any right to, but it was like part of us, so we had spent so much time with it.
The huge load was lowered onto a specially constructed trailer. Bruce Rule was in charge of shipping the precious mirror.
On November 18, 1947, a convoy of vehicles started out to try to deliver the mirror safely on a mountaintop 160 miles away. Oncoming traffic had been stopped or rerouted by the California State Highway Police as the width of the trailer required 3 lanes of highway. One of the greatest dangers was an inadequate bridge that had to be crossed. Weeks before, the Galvin Bridge near Capistrano had been reinforced, but no one really knew if the reinforcements would hold. The bridge seemed flimsy for the tremendous load that it was to bear. It sagged, but fortunately only 3/8 of an inch. The sun is supposed to shine in California every day, and the weatherman assured us that the 2 days required to move the mirror would be perfect. The first day was perfect, but on the second day, we ended up eventually going up the Palomar grade in a combination of snow and sleet and hail. And this was handled beautifully with a big pulling diesel in front and a pushing in the rear by the drivers who shifted gears almost by intuition or watching the exhaust smoke of the other diesel. It was really an amazing job of driving. and things arrived safely. It was with great relief and, of course, exuberance that we finally got there.
A million pounds of steel was wedded to thousands of pounds of glass. The telescope had been completed while the mirror was being ground and polished. Byron Hill, in charge of construction on Palomar Mountain, had the thrill of moving the telescope and mirror for the first time.
The telescope moves east and west parallel to the Earth's axis on the large 46-foot diameter horseshoe-shaped bearing. The horseshoe glides on thick films of oil. These oil flotation bearings have less than 1% of the friction of ball or roller bearings. For years, we had a concrete weight mounted in the mirror so that all the motions, all the mechanisms that operated could be put in operating condition and be ready for the mirror, so that when the mirror was mounted, it was ready to go, and it did. So there was to it. When photographs are being made, a small fractional horsepower motor turns the telescope slowly to the west to compensate for the Earth's rotation. The actual position at every instant is indicated by the calibrated dials. To minimize the effects of vibrations, the telescope rests on its own massive foundation, which is independent of those of the dome.
Each of the 36 mirror supports consists of 1,000 or so machine parts so carefully made and adjusted that no matter how the mirror is tilted or rotated, each support will carry its share of the weight of the mirror, thus minimizing the distortion due to deflections.
The dome can be controlled by the night assistant or by a robo-control that keeps it moving so that the dome never intercepts the light about to enter the telescope tube. The 200-inch telescope was built on a flat-topped ridge of solid granite 5,600 feet above sea level. The telescope was dedicated on June 3, 1948.
After the 200-inch Hale Telescope was dedicated, tested, and put into operation, astronomers pushed forward their investigation of galaxies. One of the first jobs with a new, more powerful instrument was a detailed measurement of variable stars that could now be observed in nearby galaxies. To locate and measure these variable stars, the astronomer must first obtain a long sequence of photographs extending over a year or more. He therefore spends a few nights each month taking photographs at the telescope, followed by many months of study of the plates at his Caltech office. To make these photographs, the astronomer takes an elevator up to a height equal to an 11-story building to the top of the telescope tube, where he can work during the night. The astronomer takes a big step into the prime focus cage. This was the first telescope large enough for the observer to ride on the moving telescope at the upper end of the tube. Light from a distant galaxy is reflected by the 200-inch mirror up to a focus in front of the astronomer as he sits in the prime focus cage. An astronomer makes little visual use of the telescope, only barely enough to identify the object he plans to photograph. He prefers to work with a permanent record of a photograph. Furthermore, long-time exposures with a sensitive plate can record the light of objects much too faint for the eye to see with the telescope. The astronomer spends much of his night looking at a guide star and guiding the telescope to obtain the sharpest possible images. With the greater collecting power of the 200-inch mirror, it was possible to find new variable stars in nearby galaxies. As a result of these studies, it was discovered that Hubble's distance scale needed to be revised upward. The distance to our neighbor in space, the great galaxy in Andromeda, was revised from 680,000 light years to a distance of over 2 million light years. The distances of the more remote galaxies were revised upward from 4 to 7 times the earlier estimate. The expanding universe was much larger than had been believed. Astronomers also examined the dispersed light of stars in a room beneath the telescope called the Coude room. Light is reflected by the 200-inch mirror through a series of mirrors down to this room. The light passes through a slit and is spread out by a grating into its different colors or wavelengths. The dispersed light is then photographed on a glass plate. Astronomers examined the spectral lines which reveal the chemical content of the stars. As a result of these investigations of the chemistry of stars, it was possible to tell the story of the evolution of stars. Stars are born from the condensation of hydrogen gas from great nebulous clouds in the spiral arms of the galaxies. They then become furnaces, which burn the hydrogen to form heavier elements, until finally, when the hydrogen is all transformed into heavier elements, the furnaces die out. If stellar evolution could be explained, perhaps galactic evolution could also be explained. Astronomers studied the strange or unusual galaxies for clues to the evolution of galaxies. They found evidences of violent changes, like explosions. There is some evidence that galaxies do in fact evolve. These were unusual objects, but not as unusual as some that were later discovered. Objects that were not known at the time the telescope was planned, or even as recently as a few years ago. We might leave the telling of that part of the story to one of the younger astronomers who participated in their discovery.
Dr. Alan Sandage was one of those astronomers.
As the 200-inch telescope was probing the sky for sources of light energy, large radio telescopes were discovering sources of radio energy. As these sources were located by radio astronomers, the optical astronomers at Palomar tried to identify them with optical images. Some of the strongest sources of radio energy were identified with stellar explosions, like the Crab Nebula. A number of other radio objects were identified with certain peculiar galaxies. These particular galaxies, photographed by the 200-inch telescope, are all strong sources of radio energy. But some strong radio sources whose location in the sky was very accurately fixed by radio telescopes could not be identified optically with any stellar explosion or any strange galaxy in the region of the radio source. Photographs taken with the 200-inch telescope revealed only ordinary star-like images, presumably inside our own galaxy. And more detailed examination of one of the plates taken of the precise region where radio emissions were coming from again revealed only a seemingly ordinary nearby star. But when the light from this so-called nearby star was dispersed and then photographed by Martin Schmidt, the photograph of the spectrum revealed a very large redshift in the spectral lines of the object, such as had never been observed before in any star within our galaxy. This is not a star, nor is it an ordinary galaxy. Like one of the hazy patches of light that was seen by astronomers in the 1920s, it is an unknown object. It is either among the most distant objects in the universe, billions of light years away, brighter in radio and light than any galaxy we have ever seen, so bright that a new source of energy must be found to explain it, or, on the other hand, it is an even stranger object, residing amongst the nearer galaxies. It was called a quasar, and since then many other quasars have been found. And so astronomy, having pushed out into space
is again at a crossroads. The next great step forward may be with the help of new electronic devices. A new cage has been added to the telescope tube behind the 200-inch mirror. Light enters this cage after being reflected for a second time by a smaller mirror at the upper end of the tube. The cage will carry, in addition to an astronomer, an electronic image intensifier, which will speed up the collection of certain astronomical data as much as 10 times and can make the 200-inch mirror, in effect, a 600-inch mirror. As an example of a potential use, a cluster of stars, which was previously slowly revealed in exposure times of 6 minutes, 15 minutes, 37 minutes, and 94 minutes, can now be revealed in detail in 10 minutes with the use of the image intensifier. The telescope and all its new electronic devices will more efficiently operate with the help of a new computer. The new breakthroughs in astronomy will be made with the help of the computer and the other electronic devices, which will increase the effective size of the telescope and speed up its operation. The Hale Telescope, like the universe, has grown and is evolving. We have not yet found the limits of the universe. We have found it to be larger than expected and have found mysterious new objects as challenging as the old. As we move further out into space in the next wave of exploration, we hope to solve some of the old problems. Possibly we will find some new mysterious objects, like the hazy patches of light or the quasars, that will draw us on further into space to even more distant explorations.